So good afternoon all of you. So today we are going to start new chapter, that is electromagnetic waves. This is new chapter, that is electromagnetic waves. So first of all, Maxwell's idea of displacement current. What is the heading? Maxwell's idea of displacement current. So in this we will learn what is the displacement current and how he came to this conclusion. Okay, so just this is a little bit theoretical with proof. Okay, see here. So first of all, Maxwell in 1864 showed that Ampere's circuital law is logically inconsistent. Okay, Ampere's circuital law is logically inconsistent. Where and how? Let's see. For that, we are going to consider one parallel plate capacitor. So see here, I am drawing the diagram. Now I will connect one battery here. This battery, and this is plate 1 and this is plate 2. Okay, plate 1 and plate 2. Now whatever the current is flowing, that is IC. Even here also IC. Now what I am doing, I am considering one loop here, you can see, and one loop here. Okay, circular loop I am considering. I am giving name this as a C1 and this as a C2. Okay, so C1 and C2 are the two loops. C1 and C2 are two loops. Now for loop C1, closed integral of B bar dot DL bar, okay, is equal to what? Mu naught IC. Yes, this is our Ampere's law. Yes, no? In moving charges and fields, we have learned this closed integral of B bar dot DL bar is equal to mu naught times charge enclosed. Yes, no? That is this. So for loop C1, I am getting B bar dot DL bar is equal to mu naught times IC. Okay. Now, this is your equation number 1. Now, for loop C2, now this C2 is lying in between what? Two plates of the capacitor. So in between these two plates, there is no flow of current, and that's why closed integral of B bar dot DL bar for this loop C2 is equal to 0. Okay. Yes. Now these two integrals are what we can say either side of the plate P1. Yes, no? Means C1 is this side and C2 is this side. Yes. So they must be consistent, but what we found that they are not consistent. So what Maxwell did, I am writing this line. These two integrals in equation 1 and 2 are taken on either side. Either side means one is between and one is one side. Yes, no? Either sides of the plate P1 so they must be consistent, but we find that they are inconsistent. Okay. Now, to remove this inconsistency, what this Maxwell did, to remove this inconsistency, Maxwell introduced an additional current that is ID is equal to epsilon naught d phi by dt, and this is called displacement current. Okay, and that's why therefore Maxwell's modified Ampere's law, or Maxwell modified Ampere's law into the form closed integral of b bar dot dl bar is equal to mu naught into IC plus ID, and that is equal to mu naught this IC plus this ID, whatever we got, epsilon naught d phi e by dt. Okay, where IC, you know, IC is what? Conduction current. And this above equation, or this equation, we can say b bar dot dl bar, this one is nothing but what? Ampere Maxwell law. This equation, whatever it is, I'm going to write on next page. So closed integral of b bar dot dl bar is equal to mu naught into IC plus ID is called Maxwell or Ampere Maxwell law. What is this? Ampere Maxwell law. Now for loop C1, for loop C1, phi E is equal to 0, and therefore displacement current is equal to 0, and hence closed integral of C1, that is b bar dot dl bar is equal to mu naught epsilon naught into d phi E by dt. So here IC is conduction current so IC is equal to 0 in vacuum, and IC is not equal to 0 in dielectric. So this IC is not equal to 0 in only conductors. Okay. Vacuum, or here I am writing dielectrics. Okay. So IC is equal to 0 Now one more term is we have, that is id. So id is equal to 0 in conductors and id is not equal to 0 in vacuum or dielectrics. Okay, so that's why whatever these terms we are getting, that we have to use. Okay, so that's why for loop C1 also you are getting only mu naught epsilon naught d phi by dt. Why? Because this displacement current is going to be 0 there. Yes. Okay. Now, what is the definition of this displacement current? Do you want to note down once? Okay. Note down first this page. This is second page.
Can you show the first page again? Answer.
Okay. This is second page. Yes, finished. This is third page. And you will have doubt here, id is equal to 0. Then also you should get mu naught ic, no. Then also I wrote here epsilon naught d phi by dt, because this conduction current is equal to displacement current here. And that's why IC value mu naught epsilon naught d phi by dt in magnitude. Okay. So this you keep it in mind. Conduction current, where it is zero and where it is not zero. Whereas this displacement current is zero in conductors and non-zero in vacuum or dielectrics. This part is important. Okay. Yes, finished. Now see. Whatever diagrams you have drawn before, where here, this diagram only. Now see, first conduction current IC is equal to dq by dt. Okay, from diagram. Okay, which diagram? Which I just shown you now. The diagram, if you want, you can draw here. So IC is equal to dq by dt. This is conduction current. Let's call this as equation number 1. Now electric field. Now electric field between capacitor. But we have E is equal to, we know, sigma by epsilon naught. Yes, no. So this is equal to Q by A into epsilon naught. Okay. Right. Now flux phi. Now flux phi is equal to E into A. So that is equal to Q by A epsilon naught into this A, and then you are getting here, it is equal to Q by epsilon naught. Now displacement current ID is equal to epsilon naught into d phi by dt, d phi by dt, and this is equal to epsilon naught into dq by dt into this epsilon naught. This epsilon naught and this epsilon naught will get cancelled, and you are getting ID is equal to dq by dt. This is your equation number 2, and therefore from equation 1 and 2 I can say that IC is equal to ID. Okay, so this is what displacement current and conduction current both are same. Understood? Clear? This conduction current is due to the charge flow through the wire. Yes, and that's why I have written dq by dt. Whereas when we are dealing in between the capacitor, you have electric field. That electric field is sigma by epsilon naught. Then this is sigma we have replaced. This is A, that is flux is equal to E into A. You find out this flux and then substitute this d phi by dt value in this displacement current, cancel this epsilon naught. Again, you will get ID only. Yes, and that's why I can say that conduction current is equal to displacement current. Okay, so note down. Note down. Let's move ahead. Now, Maxwell's equation. First one, closed integral, that is surface integral E bar dot ds bar is equal to q by epsilon naught. Yes, this you know. This is what, Ray? Gauss law in electrostatics. Yes. Gauss law in electrostatics. Second one, again this is also surface integral b bar dot ds bar is equal to 0, and this is Gauss law in magnetism. Okay, Gauss law for magnetism. Next one, closed line integral E bar dot dl bar is equal to d phi by dt. This is Faraday's law. This is what? Faraday's law. And number 4, which we have learned just now, again this is also line integral b bar dot dl bar is equal to mu naught into bracket ic plus epsilon naught d phi e by dt, and this is what? Ampere Maxwell's law. Ampere Maxwell law. So these 4 are the equations of this, or Maxwell's equations, we can say. These 4 are the Maxwell's equations. So you just keep it in mind. First 2 are surface integral, next 2 are line integral. Okay, note down. Why we are learning this? Because these equations will only tell us the existence of electromagnetic wave. That is what we are going to discuss in next part. First, you note down this. Okay. Okay. So let's move ahead. Now, existence of electromagnetic waves. In vacuum from Maxwell's equation. Okay. The first equation we have, that is closed integral B bar dot dl bar is equal to mu naught epsilon naught d phi by dt. Yes. And this is Ampere's law in free space. Okay. Right. And another equation we have, closed integral of E bar dot dl bar is equal to minus d phi by dt. Okay. Here also you write minus this one. Okay. You write here. Here also minus you write. Next. This is what? Faraday's law. Yes. What is this? Faraday's law. Let's call this as equation number 1 and let's call this equation number 2. Now, from first equation, what we can conclude, you see, from equation 1, time varying electric field, EF means electric field, okay? The time varying electric field gives rise to a magnetic field, okay? And equation 2, which is totally opposite to the first one, that is what? Time varying magnetic field gives rise to a electric field, okay? Therefore Maxwell suggested that a wave of electric and magnetic field exists, and such a wave is called which wave? Electromagnetic wave. Okay, so this is what all about this introductory part of electromagnetic wave, how the electromagnetic wave are going to be exist in vacuum also. Yes, that's why all these, what you can say, theoretical concepts with some proofs from some scientist. Yes. Okay, so note down this. In tomorrow's class we will learn how the electromagnetic waves are propagating, what is amplitude, then frequency, wavelength, all these things about electromagnetic waves, their properties. Okay, got it? So note down fast. We will stop here today. Okay.